Okay, so good morning. I think attendance थोड़ा कम है शायद, हाँ? Any? So today I think this is the last topic from complex variable calculus of complex variable, which is power series. Okay, so there are two kind of series that we study. One, when we look at summation from 0 to infinity. Another one when we look at summation from minus infinity to plus infinity, right? So basically negative powers and positive powers, both. So that is known as Lorentz series, when we look at both powers, negative and positive. And Taylor series is a positive power, summation from n is equal to 0 to infinity, right? So given an analytic function, or when function, a complex variable function is there, when we can say that there is a power series expansion like this, right? And later on you will see that Lorentz series can be used to classify singularities. So just by looking at the Lorentz series, you can find out the singularities in the function. Okay, so those are some beautiful results. I am not going to prove anything about Lorentz series. Probably I will give you a sketch of the proof of Taylor series. Okay, for the complex variable. Okay, and after that we will look at some of the applications. Okay. And that's all for complex variable. Okay, so let me start. Okay, power series of f of z. So a series of the form summation n is equal to 0 to infinity an z minus a raised to power n, so which is something like a0 plus a1 z minus a plus a2 z minus a whole square and so on. This is a power series, right? So we say that series is convergent actually. So basically, first of all, you know that we have talked about radius of convergence, right? If there exists a positive number r such that series is convergent for mod of z minus a less than r, then r is known as radius of convergence. Right? So series is convergent if mod of z minus a less than r, divergent for mod of z minus a greater than r, and for mod of z minus a is equal to r, it may or may not convergent. Okay. And I think the formula, as you know from the real series, right? What was the formula? Limit n tends to infinity mod of, yeah, whatever. So you remember that. That's similar formula works here also. That's not an issue, right? Find the radius of convergence. So let us look at some examples. So the only difference actually in the power series with the real variables was that the the reason for which the series was convergent was an open interval, right? Minus r to r, right? X lies between minus r to r. Here it is actually basically a circular disk, right? The reason is a circle. That's why it is known as circle of convergence. Okay. So look at an example. Log of 1 plus z is equal to z minus z square by 2 plus z cube by 3 minus 1 raised to power n minus 1 z raised to power n by n, where mod of z less than 1. So here the radius of convergence is 1. This series is convergent for. So here actually a is equal to 0 and r is equal to 1, right? Similarly, we have 1 plus z raised to power p, 1 plus pz plus p minus 1 divided by factorial 2 into z square dot 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 p minus 1 dot 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 p minus n plus 1 divided by factorial n z raised to power n. This series is convergent for mod z less than 1. So here radius of convergence turns out to be 1. Right. So all these results, just like in the case of real variables. So now the question is, how do we find this power series? Expansion of a function, complex variable function. So the first result, which is known as now Taylor's series, I'm going to give you a sketch of the proof. Why do we do that? And you will see that Cauchy's integral formulas are quite useful in finding these things. Okay, so let me show you. Suppose f of z is, so let f of z be analytic inside and on a simple closed curve C. Now suppose A and A plus H are 2 points. A and A plus H are 2 points inside C. Then Taylor series says that f of A plus H is equal to f of A plus H times f dash of A plus H square times f double dash of A divided by factorial 2 and so on, H raised to power n divided by factorial n, another derivative of A and so on. Okay. If you write z is equal to A plus H, that means H is nothing but z minus A. The whole thing becomes f of z is equal to f of A plus f dash of A times z minus A plus f double dash of A divided by factorial 2 z minus A whole square and so on. So this is known as Taylor series, right? Now you can see that, this looks like, is it familiar to you, these terms from Cauchy integral formula? Something like this appears, right? So actually you see the connection here, how do we do that? Okay, so anyway, so let me give you some idea about how do we arrive at this. By the way, yeah, one more thing. For A is equal to 0, it is known as Maclaurin series, right? And the radius of convergence of this series is mod of z minus A less than r, where capital R is the radius of convergence. Okay. Okay, so let me give you the sketch of the proof. Suppose this is our simple closed curve C, and suppose z is any point here in the simple closed curve C. I have to find the Taylor expansion at this point of the function f of z. Now I am going to construct okay, a circle centered at radius a. I mean ये ठीक से बना नहीं है, but I think you can see it. A is that center of the circle, okay, and Z is inside this circle. Then by Cauchy integral formula, f of z will be what? 1 over 2 pi I integration along C1 f of w minus z dw, right? Cauchy integral formula से directly I can find out this value, right? Because analytic है and all those things are there, right? Anyway, so now what I am going to do now, some algebraic manipulation. 1 over w minus z is nothing but 1 over w minus a minus z minus a. Do you agree? I am only looking at in this integral this portion here, 1 over w minus z, right? So 1 over w minus z is 1 over w minus a minus z minus a, which is same thing as 1 over w minus a common, 1 divided by 1 minus z minus a, w minus a, correct? Now, do you remember a series? If there is 1 divided by 1 minus z, that can be, so basically you can divide 1 by 1 minus z and you can expand in the kind of a series form, right? When you keep on dividing, right, as a polynomial. So we can say that the whole thing is 1 over w minus a 1 plus z minus a divided by w minus a plus z minus a divided by w minus a whole square plus z minus a divided by w minus a, so whole raised to power n minus 1 plus z minus a divided by w minus a whole raised to power n 1 over 1 minus z minus a divided by w minus a. Right. This is just a mere division, right? So now I can substitute this thing here, or what, rather than that, I will just multiply the whole thing by f of w on both sides. Multiply by f of w on both sides, right? And then using this equation, I can call it equation number 1 here. We are going to get this, that f of z, okay. So basically, okay, I mean I can simplify it. So 1 over w minus z is equal to, first of all, 1 over w minus a plus z minus a divided by w minus a whole square plus z minus a whole square divided by w minus a whole cube, z minus a whole raised to power n minus 1 divided by w minus a raised to power n plus z minus a divided by w minus a raised to power n times 1 over w minus z. Okay, here I am multiplying both sides by f of w and using equation 1 and kind of integrating. So we will get f of z is equal to 1 over 2 pi I integration along C1 f of w divided by w minus a dw plus z minus a divided by 2 pi I integration along C1 f of w divided by w minus a whole square dw dot 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 z minus a whole raised to power n minus 1 divided by 2 pi I integration along C1 f of w divided by w minus a whole raised to power n dw plus a last term which I am calling it un. What is un? Okay, so what I have done, basically I have just multiplied both sides by f of w and we have done the sort of integration. Then I am using the formula, right? So we got this much. What is un, which I am writing? Rest of the things are there. So essentially you will see that you will find we are getting coefficients continuously, right? How we are getting coefficient? So here un is actually 1 over 2 pi I integration along C1 this quantity. Now using Cauchy's integral formula, we know that this is equal to factorial n divided by 2 pi I for n is equal to 0, 1, 2, 3 and so on. So using this formula directly in these expressions here, I can substitute, right? So I will get something like this: f of z is equal to f of a plus f dash of a times z minus a plus f double dash of a divided by factorial 2 z minus a whole square f n minus 1 term differentiation of a factorial n minus 1 z minus a whole raised to power n minus 1 plus un is this term. So what is left? You can see that using Cauchy integral formula everything is coming in place except we have this un term, right? Now can anyone suggest what should we do with un? If n tends towards infinity, we can show that un goes towards 0. So we are done, right? We will have a series, right? Now un goes to 0 means your friend will come into picture, epsilon will come into picture, right? So that's what we have to do with this. So we only want to show that as n tends towards infinity, un goes towards 0. Then we are done. Okay. So now I will observe some inequalities. I have to show that this whole thing goes towards 0, un. This is w minus a, I am sorry if it is not written properly. Z minus a divided by w minus a raised to power n, f of w divided by w minus z dw. Now again I am going to use this integration along C f of z dz less than or equal to m into L. Remember this formula I told you, L is the length of that simple closed curve and so on. Now if you note that W is on C1, we have mod of Z minus A divided by W minus A, so call it gamma. This will be less than 1. Gamma is a constant. So these observation comes, these inequalities you can observe by looking at the scenario what is happening anyway. Also, so first thing is this, second thing is this, third thing is that mod of f of w is less than m. Since fz is analytic, all those kind of things are there, right? So m is a constant. And fourth inequality I am going to use, mod of w minus z is equal to w minus a minus z minus a. This will be at least r1 minus mod of z minus a. Okay. Where what is r1? R1 is a radius of C1. So this circle here, this has radius. This is C1 actually, right? C1 has radius R1. So this is R1 here. Okay. So so we arrive at these four inequalities. Now we are ready. So this implies that mod of un is equal to 1 over 2 pi. 1 over 2 pi I, mod of I is 1, so that is not there. Then integration along C, z minus a divided by w minus a whole raised to power n, f of w divided by w minus z dw this whole thing is less than or equal to 1 over 2 pi gamma raised to power n, because you see, using this result, mod of z minus a divided by w minus a is gamma, right? So whole thing will be less than gamma raised to power n, right? And then whatever is left is integration along c f of w divided by w minus z dw, which is, then we are using this result, right? If f of z is, I mean, and this result together, right? So we are having here capital M divided by r1 minus times 2 pi r1, length of the curve, because it's a circle now, simple closed curve, which is 2 pi r1, radius is r1, right? So overall this is gamma raised to power n capital M into r1 divided by r1 minus mod of z minus a. Now gamma is less than 1, right? You can see that gamma is less than 1 here. So as n tends towards infinity, this whole thing goes towards 0, right? Because this is a dominant term, gamma raised to power n, right? The whole thing will goes towards 0, because you know gamma raised to power n goes towards 0 as n tends towards infinity, because gamma is less than 1. So that means mod of un goes towards 0 as n tends towards infinity. So you are done, right? So we have only used algebraic manipulation, and so basically this whole thing goes towards 0, means close to epsilon or whatever you want to say, right? The whole thing goes towards 0. Okay, so that's all about Taylor series. So we have this series in our hand, right? So this is an infinite series, right? So it will keep on going. Now the next series is when both powers are there, positive and negative. So if f of z is analytic, inside and on the boundary of the ring shaped region. Ring shaped means कुएं की जगत, ring shaped region. C1, so suppose this is A, this may be radius R1, this may be radius R2, right? This is C2, this is region R. Right, and Z is a point, suppose here. This ring shaped region is here. So f of z is analytic inside and on the boundary of the ring shaped region, this region, okay, R. Function analytic है यहाँ पे, right? तो जो smaller circle है उसका radius R2 है, bigger circle है उसका radius R1 है, right? A is the center and all that. Z is a generic point which you can move along in the region, right? And C1, C2 are the curves which are enclosing it. Or basically concentric circles. So C1, C2 are circles, yes. Okay. And I am assuming that R1 is greater than R2. The radius of first circle is bigger than the second circle. Then for every Z in R, what is R? Sorry. Yeah. So for every Z in this region R, Z is moving in this region R, right? we have f of z is equal to summation n is equal to 0 to infinity a n z minus z naught raised to power n plus summation n is equal to 1 to infinity a minus n divided by z minus a raised to power n. Positive power and negative power, where I know what are these coefficients a n and a minus n. Okay, so a n is 1 over 2 pi I integration along C1 f of w divided by w minus a raised to power n plus 1 dw, n is equal to 0, 1, 2, 3 and so on, and a minus n is equal to 1 over 2 pi I integration along C2 f of w divided by w minus a raised to power n plus 1 dw, n is equal to 1, 2, 3 and so on. So both these coefficients are expressed in terms of Cauchy's integral formula, right? So you know, so a n is in terms of Cauchy integral formula, a minus n is in terms of Cauchy integral formula. Sometimes some people combine and write it at summation from minus infinity to plus infinity. Also you can write, right? You can switch this if you want, right? माइनस n को यहाँ ले जाएंगे तो ये माइनस इन्फिनिटी से प्लस इन्फिनिटी चला जाएगा, राइट? नेगेटिव नंबर्स. So I can, so how will you prove it? Again by Cauchy integral formula, fz is analytic, so basically f of z is nothing but 1 over 2 pi I integration along C1 f of w divided by w minus z dw minus 1 over 2 pi I integration along C2 f of w divided by w minus z d omega. So here you have to expand this and use it here just like in the previous case, right? 1 over w minus z is equal to 1 over that a के terms में लिख करके expand करके. So I am not going to do that. So one thing I should want to mention here, this is known as analytic part of the series and this is known as principal part. So actually this principal part will tell you what kind of singularity is there. Okay. So by the way, now normally people say that okay, given a function find out the Lorentz series expansion. So we are going to use known formulas that you know, right? Suppose you are able to find Lorentz series expansion for say 1 over 1 minus z. If function is 1 over z, oh f of z is equal to 1 over z minus 1, right? Or 1 minus z, whatever. You can find the series expansion, right? Normal series expansion, right? Provided mod z less than 1 and all those kind of conditions, right? So those kind of tricks people use to basically find that series expansion. Okay. So some known series in practice, I mean they don't always compute this Cauchy integral formula. Using a known series, substitute it and then try to find a series, right, expansion. Let me give you some examples actually now. Okay, so if f of z is equal to log of 1 plus z, right, so Taylor series अगर निकालनी है around the point z is equal to 0, so a is equal to 0 here. So we know that f of z is equal to log of 1 plus z equal to f of 0 plus f dash of 0 times z plus f double dash of 0 times z square divided by factorial 2 and so on is equal to z minus z square by 2 minus z plus z cube by 3 minus z is power 4 by 4 and so on. aa gaya, right? So this is the वन वे ऑफ फाइंडिंग द टेलर सीरीज. सेकेंड वे क्या है? अब देखो यहां पे so we know that since so this is one method. Since for mod z less than 1 over 1 plus z is equal to 1 minus z plus 1 over 1 plus z is equal to 1 minus z plus z square minus z cube. राइट ये सीरीज मालूम है? राइट सपोज यू फाउंड दिस सीरीज. इसका इस्तेमाल करके आई कैन फाइंड दैट log 1 plus z. हाउ? एनी आइडिया? अगर इसको इंटीग्रेट करेंगे तो क्या आएगा? log 1 plus z आएगा ना. ऑफ कोर्स व्हाट वेरिएबल यू शुड व्हाट लिमिट यू शुड टेक, राइट? एंड यू सी. So we integrate from 0 to z on both sides. So 1 over 1 plus z will be what? Log 1 plus z, right? And this will be what? 1 will become z, z will become z square by 2 and so on, right? Integration के बाद. So essentially you will get log 1 plus z is equal to z minus z square by 2 plus z cube by 3 minus z is power 4 by 4 plus and so on. So there are so many ways you can do. एक सीरीज का इस्तेमाल करके दूसरी सीरीज को निकालना बहुत कॉमन प्रैक्टिस है, राइट? एक मालूम है और दूसरे में यूज करना, राइट? ऑफ कोर्स यू नीड टू मेक श्योर दैट वट एवर यू आर डूइंग इज वैलिड, राइट? कुछ ऐसा नहीं है कि कुछ इशू हो, राइट? तो दिस इज वेरी कॉमन, राइट? इंटीग्रेट कर दिया इसको, ठीक है? या सिमिलरली द वे यू यूज टू डू इन द रियल केस, सेम थिंग हैपेंस हियर आल्सो, राइट? Okay. Now classification of singularities. From Lorentz series expansion, actually we can find out, we can do the classification. First of all, poles. So poles, you know, remember that 1 over z minus a is, so z is equal to a is a pole of order 1, right? Those kind of things are there. Or 1 over z minus a whole square, in that case z is equal to a is a pole of order 2, right? I've shown that definition earlier, right? But actually just by observing the Lorentz series expansion you can find out, because what kind of terms are here, right? Suppose there are k terms negative पावर में, राइट? z माइनस a is for k तक हो terms. That means there is a pole of order k. Just by looking at this expression, how many terms are there, right? अगर z माइनस a का एक ही टर्म है यहाँ पे 1 over z माइनस a का, तो pole of order 1. दो टर्म है तो ऑफ कोर्स z माइनस a का होल स्क्वायर भी आ जाएगा, तो pole of order 2, right? तो certain number of terms, just by observing Lorentz series we can say that how many poles are there of certain order. So for example, if Lorentz series में, in Lorentz series we have finite number of negative power terms, right? So for example, so a minus 1 over z minus a plus a minus 2 over z minus a whole square, a minus n over z minus a whole is for n. Of course, largest one non-zero होना चाहिए, right? Otherwise there will be issue, right? So in that case, z is equal to a is a pole of order n. अगर a minus n 0 है तो या उसके पहले वाला है, मान लो ये नॉन जीरो है बाकी सारे जीरो हैं, so there will be a pole of order 2, right? Okay, so depending upon, तो ये नॉन जीरो होगा तभी तो ये टर्म होगा, अदरवाइज ये टर्म ही नहीं होगा, right? So z minus a whole is for n. So if there is a finite number of negative terms, then there is a pole of order n. Okay, I think other one was removable singularity, although I talked about it, right? Removable singularity, if f of z is not defined at z is equal to a, but limit exists, then a is called removable singularity. This is easy. So somebody may ask, example, find Laurent series expansion about z is equal to 1 and name the singularity. Function क्या है? e raised to power 2z divided by z minus 1 whole cube. कैसे करेंगे? इस फंक्शन का e raised to power 2z divided by z minus 1 whole cube का लॉरेंट सीरीज एक्सपेंशन फाइंड करना है around the point z is equal to 1. Any idea what to do? चाय वाय लेके बैठना पड़ेगा. It's so simple ना. What we need to do now? अगर हम z का सीरीज एक्सपेंशन कर देंगे तो वो तो z is equal to 0 के अलॉन्ग हो जाएगा, राइट? हमको चाहिए z is equal to 1 के अलॉन्ग. So what we should do? So suppose z minus 1 is equal to u, क्योंकि z minus 1 के अलॉन्ग करना है, right? So that means z is equal to u plus 1. सब्स्टिट्यूट कर दो इसमें और u का 0 के खिलाफ एक्सपेंशन ले लो तो वो हो जाएगा z is equal to 1 के खिलाफ, right? So we can just say that means the whole function will be so e raised to power 2z divided by z minus 1 whole cube is equal to e raised to power 2 plus 2u divided by u cube. This is nothing but e square divided by u cube into e raised to power e square divided into e raised to power 2u divided by u cube is equal to e square divided by u cube. e raised to power 2u को एक्सपेंड कर लिया 1 plus 2u plus 2u whole square divided by factorial 2 2u whole cube divided by factorial 3 and so on. मल्टीप्लाई कर दिया e square divided by u cube plus e square I mean 2e square divided by 2 u चला जाएगा ना, I mean मैं डायरेक्टली लिख देता हूँ, ठीक है? e square divided by z minus 1 whole cube plus 2e square divided by z minus 1 whole square. Why? Because z minus 1 is equal to u. I can substitute that, right? Plus 2e square divided by z minus 1 plus 4 times e square divided by 3 plus 2e square divided by 3 z minus 1 and so on. So now you can see that just by making this substitution z minus 1 is equal to u, I have found a series which is around z is equal to 1, right? So what is a singularity here? Pole of order. What is the highest order? 3. So it's a pole of order 3. Right? So these kind of manipulations are often useful, right? Series दिया हुआ है and then you have to find around some point, say z is equal to a. So z minus a is equal to theta डाल करके theta में expansion कर दो, u कर दो, whatever, right? And then you expand the series, right? It is a pole of order 3. Okay, I think now we are ready. What is known as residues. Very important result and very useful result. So suppose f of z is single valued and analytic inside and on C, a simple closed curve at z is equal to a, you know. So then we have f of z is equal to summation n is equal to minus infinity to plus infinity a n z minus a raised to power n, where a n is written as 1 over 2 pi I. This is a compact formula, integration along C, f of z divided by z minus a whole raised to power n plus 1, where n is 0 plus minus 1 plus minus 2 and so on. दोनों को एक साथ लिख दिया, right? Summation minus infinity is plus infinity. This is the, you know, compact formula for Lorentz series, right? So, and where a n is this thing, right? You can see that here n is positive, 0 as well as negative, right? So all terms will come there, right? Everything is taken care of. So for n is equal to minus 1, we have integration along C, f of z dz is equal to 2 pi I a minus 1. Okay, you can see that. So I think 2 pi I a minus 1. Can you see that from here? If I put n is equal to minus 1, z minus a का term नहीं रहेगा, right? And what we are left with, this integration along C, f of the dz is equal to 2 pi I times a minus 1, right? This is really useful thing. This quantity a minus 1, which is the coefficient, is known as residue. So normally क्या है, ये singularity का होता है residue. Let me show you. Okay, so basically, so this is residue of f of z. Okay, a minus 1 here is a residue of f of z at the point z is equal to a. Okay, the question is, how do we find a minus 1 in general? So of course, I mean, you can say that, okay, I can integrate these things and, you know, compute this, but there are simpler methods available. Let me show you. Residue of f of z at z is equal to a. Okay, so yeah, I think I forgot about to write here except at a. So here actually we have given, so f of z is single valued analytic function inside and on a simple closed curve C, except at point z is equal to j, which is a singularity, right? Z is equal to j, except at z is equal to a. I forgot to write except word anyway. So then we can actually compute residue at this singular point if by substituting n is equal to minus 1, we get this quantity. So basically one way is this, that a minus 1 is nothing but 1 over 2 pi I integration along C, f of z dz. This is our residue, right? Now how do we calculate this residue? So actually a minus 1 is nothing but limit z tends to a 1 over factorial k minus 1, k minus 1th derivative of z minus a raised to power k f of z if z is equal to a is a pole of order k. If f of z has a pole at z is equal to a of order k, मतलब लॉरेंस सीरीज के एक्सपेंशन में फाइनाइट टर्म्स का हाईएस्ट ऑर्डर होगा k का, राइट? z माइनस a रेज़ टू पावर k होगा, राइट? एंड सम फाइनाइट नंबर ऑफ टर्म्स होंगे देयर. सो नाउ एक्चुअली इफ यू मल्टीप्लाई दिस f of z, जो सीरीज का एक्सपेंशन है, उसको z माइनस a रेज़ टू पावर k से और डिफरेंशिएट कर दो k माइनस 1, तो जो जहां पे जो हाईएस्ट ऑर्डर होगा वो वैल्यू बाहर आ जाएगी, बाकी सब तो चला जाएगा ना, जीरो हो जाएगा. एंड देन यू कैन मल्टीप्लाई विद दिस टू गेट द एग्जैक्ट वैल्यू ऑफ a minus 1. सो लेट मी शो यू. So what we can do here, since f of z will be something like this, a minus k divided by z minus a whole raised to power k plus a minus k plus 1 divided by z minus a whole raised to power k minus 1, okay, plus dot 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 a minus 1 divided by z minus a plus positive part. I don't know what, I don't care about positive part, but anyway. So we have negative terms, finite, and the highest is k in the Lorentz series, right? Then that's why, because there is a pole of order k. Now what I can do, if I have to find a minus 1 from this expression, हमको क्या करना पड़ेगा? एक बार डिफरेंशिएट करेंगे, दो बार करेंगे, तीन बार करेंगे, k minus 1 टाइम्स हमको डिफरेंशिएट करना पड़ेगा, एंड देन वी टेक द लिमिट एज z टेंड्स टू a, राइट? देन ओनली वी कैन, एंड देन वो स्केलिंग फैक्टर बाहर आ जाएगा ना, डिफरेंशिएशन का जो है ना 1 over फैक्टोरियल के टर्म्स में आएगा. सो आई थिंक दैट इज प्रीटी स्ट्रेट फॉरवर्ड. बट सो व्हाट आई एम गोइंग टू डू, मल्टीप्लाई दिस बोथ साइड बाय z minus a whole raised to power k. बोथ साइड अगर हमने, बिकॉज ये हाईएस्ट पावर है, इससे दोनों तरफ मल्टीप्लाई कर देंगे, दिस इंटू दिस इज इक्वल टू, सो ये कट जाएगा, a माइनस के रह जाएगा, यहां पे, यहां क्या रह जाएगा, z माइनस a का एक टर्म रह जाएगा, राइट? एंड लाइक सो ऑन, यू कैन कीप ऑन डूइंग दिस, राइट? So after multiplication, so basically what we are doing, multiply both sides by z minus a whole raised to power k and differentiate both sides k minus 1 times. Because what will happen, हम बाकी टर्म्स की चिंता नहीं कर रहे हैं. यहाँ पे क्या होगा, जब हम z माइनस ए की होल रेज़्ड टू पावर k से मल्टीप्लाई करेंगे तो यहाँ पे एक टर्म आ जाएगा z माइनस ए होल रेज़्ड टू पावर k माइनस 1. अब हमको a माइनस 1 की वैल्यू चाहिए है, तो इसको k माइनस 1 को डिफरेंशिएट करना पड़ेगा पहली बात तो, तब तो ये गायब होगा ना, तो खाली कांस्टेंट बचेगा. एंड देन व्हेन वी टेक द लिमिट एज z टेंड्स टू a, बाकी सारे जीरो हो जाएंगे, केवल यही बच जाएगा, राइट? गॉट इट? दैट्स समथिंग विद इजी कैलकुलेशन. So what we get here is that if you differentiate k minus 1 times z minus a whole raised to power f of z k, you get something like this, factorial k minus 1 a minus 1 plus k times k minus 1 and so on, right? हम तो खाली इसकी चिंता कर रहे हैं, बाकी हमें कोई मतलब नहीं है. If we take limit z tends to a, बाकी सब में एक्चुअली z माइनस a का टर्म आएगा, सो वो सब जीरो हो जाएगा, राइट? सो व्हाट इज लेफ्ट इज a माइनस 1, राइट? सो बेसिकली दिस वैल्यू इज नथिंग बट फैक्टोरियल k माइनस 1 टाइम्स a माइनस 1. सो फ्रॉम हियर आई कैन फाइंड आउट द वैल्यू ऑफ a माइनस 1. सो बेसिकली a माइनस 1 इज दिस क्वांटिटी. So if Lorentz series has finite number of negative powers, highest power is suppose order k की, अब मतलब k है, then there is a pole of order k, and I can compute, whenever there is a pole I can compute the residue, and the residue can be calculated by just using this formula, right? Multiply f of z with z minus a whole raised to power k, differentiate k minus 1 times, divided by 1 over factorial k minus 1, and you will get the value of residue at that singular point pole a minus 1, right? Now I think I will show you some applications of this in for example in integration, and also in terms of some of the summation of the series. So I need to only talk about the applications that is left, probably 15 to 20 minutes next class, and then we are done with the complex. Thank you. you.